Roman engineers and legionnaires paved roads through impassable mountains, erected amphitheaters for tens of thousands of spectators in a matter of years, and built entire military fortresses in a few hours. Their methods were so effective that many of their creations, from roads to aqueducts, are still in use today, 2 millennia later. It was not magic or divine intervention, but cold calculation, impeccable organization, and a few engineering secrets that were lost for a long time. Watch the video to the end, and you will learn how the Romans managed to stay ahead of their time. What secret material allowed them to build underwater, and why a disciplined legionnaire with a shovel was more formidable than a legionnaire with a sword. I will reveal the most closely guarded secret of Roman engineers, and it is not about any one invention. While the Greeks sought to create a unique, one-of-a-kind masterpiece in every temple, the Romans professed a different philosophy, the philosophy of absolute standardization. It was this approach that allowed them to copy and paste cities, bridges, and roads throughout the empire at an incredible speed. Their main goal was not uniqueness, but functionality, speed, and durability, multiplied by scale. For the Roman state, engineering was as much an instrument of power as legions or laws. A road built in a wild province immediately turned it into part of Rome. An aqueduct supplying water made life in a new city as comfortable as in the capital. This utilitarianism was elevated to an absolute, where every engineer and every architect was first and foremost a civil servant. Instead of inventing something new for each project, the Romans refined and replicated the best solutions. They took the arch from the Etruscans and turned it into a universal building block from which anything could be assembled, from a bridge to the Colosseum. They did not build 100 different bridges. They built the same type of bridge 100 times, bringing the process to the point of automatism. This unification saved time on design and training. Every Roman engineer, or architectus, underwent rigorous training based on proven manuals and principles. They used a single set of tools and a single system of weights and measures. Thanks to this, an engineer from Syria could easily lead construction in Britain. All drawings and plans were understandable, and construction methods were identical throughout the empire. This standardization applied not only to large projects, but also to the smallest details. The size of bricks, the composition of mortar, the width of the roadbed, all of this was regulated. This approach made it possible to calculate the required amount of materials and labor in advance. Logistics, not just construction, was Rome's strong point, and it was based precisely on these standards. Practicality was their highest virtue, and this is evident in everything they did. If, for example, to achieve the goal of laying a straight road, it was necessary to demolish a hill or dig a tunnel, they did so. They did not look for detours, but subjugated the landscape to their will in their designs. This straightforwardness was not only engineering, but also political. That is why we see so many Roman colonial cities that are similar to each other, built according to a single model. A rectangular grid of streets, a forum in the center, a standard set of public buildings, baths, a theater, a temple. When a legion arrived at a new location, it did not have to think about how to plan the city. It already had a ready-made template that only needed to be implemented. The Romans were the first in history to create a system in which engineering knowledge was separated from specific craftsmen and turned into a replicable state resource. They created an engineering conveyor belt, 1,500 years before Henry Ford. This system was capable of reproducing complex objects with predictable quality and within specified timeframes. Ultimately, the speed of Roman construction was not the result of the genius of individuals, but of the flawless work of the system. Organization, logistics, standardization, and an almost endless supply of disciplined labor. The Romans built quickly not because they were geniuses, but because they turned construction into a science as precise as warfare. Is this obsession with standardization a sign of genius or a lack of creativity? Share your opinion in the comments. I'm very interested to hear your point of view. And don't forget to subscribe to see how this philosophy was applied in practice. And which army was the most powerful construction corporation in history? Are you ready to learn the truth about what Roman legionnaires actually did for most of their service? We tend to imagine him as a warrior clad in armor, sword at the ready. However, the reality was much more prosaic. Legionnaires spent most of their time not with swords, but with shovels, pickaxes, and saws. It was the army that was the main construction force of the empire. Each Roman legion, numbering about 5,000 men, was not just a combat unit, but a fully autonomous engineering brigade. On campaign, each legionary carried not only weapons and armor, but also an impressive set of construction tools. This set included a pickaxe known as a delabra, a basket for carrying earth, a saw, and several pointed stakes for palisades. This emphasis on engineering work was embedded in the very foundation of Rome's military doctrine. The legions did not simply fight, they bit into the conquered territory, securing it with infrastructure. They built roads to move quickly, bridges to cross rivers, and fortresses to control the terrain. Each military campaign was also a large-scale construction project. There was strict specialization within the legion. In addition to ordinary soldiers who dug trenches, there were so-called immunes, specialists who were exempt from routine guard and maintenance duties. These included engineers, surveyors, carpenters, masons, blacksmiths, and even craftsmen who made siege engines. The legion could build anything using only its own resources. The discipline that made the legions invincible in battle worked just as well on construction sites. Soldiers worked in shifts, in strict order, fulfilling quotas. The work did not stop for a minute. While some cohorts were digging, others stood in battle formation, guarding their comrades. This organization allowed them to achieve phenomenal speed. The Roman commander did not depend on civilian contractors who needed time to gather and deliver workers. All he had to do was give the order, and thousands of trained, disciplined, and physically strong men immediately set to work. This mobility and autonomy gave Rome a huge advantage over any opponent. Engineering training was a mandatory part of every soldier's education. Recruits learned not only to march and fight, but also to dig trenches, build ramparts, and construct bridges. A soldier who could not wield a shovel was considered as useless as one who could not wield a sword. These were the two wings of the same profession. It was the legions that built most of the famous Roman road network. Soldiers cut through forests, leveled the ground, laid a multi-layered foundation, and paved the surface. The road was built to military standards, straight, sturdy, capable of withstanding the weight of heavy carts and the rapid march of thousands of soldiers in any weather. The most striking example of their speed was the construction of military camps, which we will discuss in more detail. But even large permanent structures, such as Hadrian's Wall in Britain, were built by 3 legions. The soldiers did not just stand on the wall, they built it, from the foundation to the battlements. This military machine was powerful, but what did it build? In the next chapter, we will talk about the material that allowed them to build not just quickly, but for millennia. Are you ready to learn about Roman concrete, which was stronger than ours and could set underwater? What I am about to show you literally changed the world, and this secret was lost for 1,500 years. When we say Rome, we imagine marble columns, but the real revolution in construction was not related to stone, but to a completely different material. We are talking about opus cimentitium, or Roman concrete, an invention that allowed them to build faster, cheaper, and in ways that were previously unimaginable. The Romans did not invent concrete. Primitive forms of it existed before, but they perfected its formula, creating a material that surpasses even modern Portland cement in many respects. The secret lay in one unique component, pozzolan, or volcanic ash. This ash, mined in large quantities in the Naples area and Mount Vesuvius, had amazing properties. Unlike modern concrete, which is simply a mixture of cement, sand, and gravel, Roman concrete was a chemically active mass. When pozzolan was mixed with lime and water, a chemical reaction occurred. New, incredibly strong, crystalline compounds were formed, which literally fused the mixture into a monolithic stone. The most striking property of this mixture was its ability to harden without access to air, including underwater. Modern concrete needs air to gain strength, but Roman concrete performed perfectly well in water. This allowed them to build massive port piers, bridge supports directly in the beds of turbulent rivers, and aqueducts without fear of moisture. The construction technology was also ingeniously simple and fast. The Romans did not pour liquid concrete as we do today. They built wooden or brick formwork and then laid the mortar in layers. A layer of thick mortar, then a layer of rubble or construction debris, then mortar again. This method, called rubble masonry, was incredibly economical. This type of construction did not require a large number of highly skilled masons who were needed to build walls from hewn stone. All that was needed was an army of unskilled but disciplined workers who could build formwork, carry water, mix mortar, and lay stones. This was ideal for the use of legionnaires or slave labor. Thanks to concrete, the Romans were able to fully realize the potential of arches and vaults. They created huge spans and gigantic domes, such as the Dome of the Pantheon in Rome, which remains the largest unreinforced concrete dome in the world. It would have been impossible to create such a structure out of stone. Concrete allowed them to sculpt space. Roman concrete was not only strong, but also surprisingly durable. Modern research shows that over time, it does not deteriorate, but only becomes stronger. Seawater penetrating the structure reacts with pozzolan, forming new minerals that heal microcracks and make the material even more monolithic. This explains why Roman port structures, which have stood in saltwater for 2,000 years, are in better condition than many concrete piers built in the 20th century. The Romans, perhaps without realizing it, created a self-repairing material. This material was cheap, quick to use, did not require high qualifications, and possessed incredible strength and durability. It allowed the Romans to move from constructing individual buildings to creating entire infrastructure systems on an imperial scale. This material was the true foundation of their engineering power. This material allowed them to create the Dome of the Pantheon, which still stands today. If you are also fascinated by this technology, please like this video. And don't forget to subscribe to the channel to see new episodes where I will reveal the incredible secrets of ancient Rome. What if I told you that roads built 2,000 years ago were designed with such precision that modern highways are laid on top of them? The Roman road network is not just a means of communication. It is a visible embodiment of imperial power and engineering thought. And the main principle of their design was an almost fanatical commitment to a straight line. When a Roman engineer planned a new road, he did not try to go around every hill or valley. His task was to connect point A and point B by the shortest possible route. If there was a mountain in the way, they dug a tunnel or built an exhausting climb. If there was a swamp in the way, they built a dam several kilometers long. The road cut through the landscape rather than adapting to it. To achieve this straightness over huge distances, relatively simple but effective tools were used. The main one was the gromata, a device consisting of two crossed slats with plumb lines at the ends. It allowed them to lay perfectly straight lines and build precise right angles. Working from one sighting point to another, surveyors or grammatici laid out the route. To determine slopes, they used a horobat, a long wooden beam, more than 6 meters long, with a groove for water, which functioned as a water level. This allowed them to maintain the necessary, albeit steep, slope on ascents and descents. Another device was the diopter, a more complex angle measuring instrument similar to a primitive theodolite. This obsession with straight lines had not only practical, but also ideological significance. A straight road cutting through the landscape was a symbol of Roman order, which had subjugated wild nature. It was a statement. Rome is here, and it is here to stay. The design process began with careful reconnaissance. Military engineers and surveyors studied the terrain, identified key points and sources of building materials. Once the plan was approved, the legions got to work. Soldiers cleared the route, cutting down forests and uprooting stumps tens of meters wide. Roman roads were built primarily for the military. Their task was to ensure the fastest possible transfer of legions and couriers from one end of the empire to the other. Commercial use was secondary, and often heavy freight cars were not even allowed on them, so as not to destroy the pavement. That is why roads often avoided the centers of existing local settlements, passing by them. This was done for speed. The legions should not get stuck in narrow streets. New cities and post stations then sprang up along the road itself, drawn to this new artery of life. Milestones, or miliaria, were placed along the entire length of the roads at every Roman mile, about 1,280 meters. These were tall stone pillars that indicated the distance to the nearest cities and to Rome itself, the golden miliarium in the Forum. This was not just navigation, but a constant reminder of the center of power. The speed of design was astonishing. An experienced team of surveyors could lay out and mark many kilometers of road in a single day. Once the line was determined, the legions began earthworks, and there was no turning back. A decision made with thunder and force became law for the landscape. But how did they manage to build these roads so that they would survive for millennia? In the next chapter, we will literally dissect a Roman road layer by layer and find out what is inside it. The Roman road, the famous Via Strata, paved road, was an engineering marvel not only on the surface but also in its invisible foundation. It was a carefully calculated system where each layer had its own meaning and function. Its incredible durability, which has allowed many sections to survive for more than 2,000 years, can be explained by its complex, multi-layered construction, thought out down to the smallest detail. It was not just a stone road, it was a monumental structure built with the same attention to detail as temples, palaces, or aqueducts. Because for the Romans, the road symbolized the power of the state in its connection with the provinces. Construction always began with earthworks, and this stage was the most labor-intensive. Soldier builders dug 2 long parallel trenches that defined the exact boundaries of the future road. Between them, they removed the entire top fertile layer of soil, often filled with roots and moisture. This strip, called a fossa, was deepened until it reached a solid, stable layer, most often rock or dense clay soil. Depending on the terrain, the depth could reach 1 meter or even 1.5 meters, because the road had to withstand not only legions, but also heavy carts with cargo. The first and roughest layer, called the statumen, was laid at the bottom of this trench. It consisted of large stones, the size of a fist or larger, and served as a kind of skeleton for the road. Thanks to this layer, water easily drained away, and the road itself did not sink. The stones were often laid by hand, selecting their shape so that they fit tightly together. For greater strength, they could be bonded with clay, lime, or even a mixture of small stones and sand. This foundation was so strong that even centuries later, it can still be found under modern roads in Europe. The next layer, the rudis, was a thinner and more precise base. It consisted of broken bricks, crushed stone, small stones, and lime, carefully mixed together. This layer was about 20 to 30 centimeters thick, and the legionnaires tamped it down to rock hardness with heavy wooden hammers. Sometimes special rollers made from solid logs were used for compaction. This layer not only strengthened the structure, but also made it waterproof, preventing moisture from penetrating into the lower layers. Next came the core of the road, the nucleus. It was a surprisingly modern mixture, reminiscent of early concrete. It consisted of fine gravel, coarse sand, and hot lime, which formed a solid, monolithic mass when dry. Workers carefully leveled and compacted this layer to achieve perfect smoothness. It was the nucleus that distributed the weight on and prevented cracks from forming. It created a flat platform on which the stones of the top layer were then laid. Only then did the final stage begin, the laying of the finishing layer, the summum dorsum, or pavimentum. Depending on the importance of the road, this layer was constructed in different ways. On major thoroughfares, such as the Via Appia, huge polygonal blocks of basalt or limestone were used, perfectly fitted together. There were almost no gaps between the stones, which allowed chariots to move smoothly and the road to remain intact for centuries. On less important roads, compacted gravel or dense sandstone was used. The entire road had a slight slope from the center to the edges, forming a characteristic convex shape that the Romans called the spina. This element was extremely important. It ensured the drainage of rainwater into drainage ditches laid along the road. These ditches, called sulci, prevented water from stagnating, thus preventing erosion and destruction of the foundation. In some cases, small stone curbs were also placed along the road to hold the soil and direct the flow of water. The thickness of such a road could reach 1.5 meters, which made it incredibly stable. Even harsh winters, frosts, and downpours could not destroy such a structure. It did not allow moisture to pass through, did not sag or crack, and plant roots could not break through the dense layers. Thanks to this, many roads have survived to this day almost in the same form in which the Roman legions marched along them. Even more impressive is that the construction of such complex roads was carried out at an astonishing speed. Disciplined legionnaires acting as a single mechanism could build hundreds of meters of paved road in a day. In the detachment, everyone performed their own task. Some dug, others carried stones, others tamped, and still others laid tiles. This order and precision were the key to Roman engineering power. It was this system, a deep drain foundation, 2 reinforcing layers, and a perfectly leveled waterproof coating with a slope, that became the secret to the durability of Roman roads. They did not simply connect cities, but became a symbol of civilization, stronger than time and the elements. The Romans did not simply build a road, they created an engineering marvel that outlived the empire itself. What the Roman army did every evening, modern engineers cannot repeat even in a week. The Roman legion on the march never, under any circumstances, stopped for the night in an open field. Every evening, regardless of fatigue, weather, or the proximity of the enemy, the legion built a fully fortified camp, or castrum. This process was so automated that it took only a few hours. As soon as the legion arrived at the place of overnight stay, which was chosen in advance by scouts and surveyors, coordinated work began. First, the grammatici marked out a standard rectangular grid for the camp on the ground. They stuck colored flags into the ground to mark the main streets, the Cartus and Decumanus, the location of the commander's tent, praetorium, and the altar. While one part of the legion, usually several cohorts, lined up in battle formation for guard duty, the rest of the soldiers immediately set to work with their dolabras. Each legionnaire was not only a warrior, but also a digger. Each detachment had its own clearly marked section of the perimeter for which it was responsible. The work began with digging a trench or fossa. This was not just a ditch, but a serious V-shaped barrier, up to 1.5 meters deep and up to 3 meters wide. All the earth extracted from the ditch was immediately passed along the chain and laid on the inner edge, forming a rampart, or agger. This rampart of compacted earth and turf was in itself a serious obstacle, several meters high. But that was not enough. A palisade, or vallum, was erected on top of the rampart. It consisted of stakes, suits, which each legionnaire carried with him in his marching gear. These stakes were sharpened at both ends and had spikes, making them ideal for a prefabricated barrier. Simultaneously with the construction of the perimeter, other teams pitched tents inside the camp. Here, too, standardization reigned supreme. Each tent, designed for 8 people, contubernium, was placed in a strictly designated spot. As a result, an hour after work began, a city with straight streets, neighborhoods, and defensive walls sprang up on the empty field. The entire process, from marking out the site to installing the last stake in the palisade, took an experienced legion 2 to 4 hours. This was a daily routine, repeated dozens of days in a row during a long march. The soldiers had dinner and went to bed in complete safety behind the walls of their own fortress. In the morning, the camp was dismantled just as quickly. The palisade was taken down, the stakes were returned to the baggage train, and the tents were packed away. The moat and rampart were often left behind, and many of these temporary camps can still be seen on satellite images throughout Europe. This skill gave Rome an incredible tactical advantage. This ability to create instant fortresses discouraged opponents. They could not catch the legion off guard at night or force it to fight on their terms. The Romans always fought with their rear and flanks covered by their own fortress, which they carried with them. The speed and efficiency of this process were a direct result of the standardization, discipline, and versatility of the Roman soldier. Everyone knew their maneuver, everyone had their tool. They did not need blueprints or lengthy meetings. This remarkable engineering routine was as much a part of their combat power as their sword skills. This speed was remarkable, but how did they supply these new cities with water, especially when building permanent fortresses in cities? In the next chapter, we will look at the marvel of engineering, aqueducts, Roman cities were synonymous with comfort, and the basis of that comfort was water. Huge public baths, thermae, fountains, private villas, and the general population consumed enormous amounts of water that could not be supplied by wells alone. The solution was aqueducts, grand structures that carried clean spring water to cities, sometimes tens of kilometers away. The popular image of an aqueduct is a majestic series of stone arches crossing a valley, such as the Pont du Gard in France. However, these bridges were only the most spectacular, but small part of the system. In fact, more than 90% of the length of any aqueduct ran underground or at ground level. Roman engineers preferred to run the canal in trenches or tunnels dug into the rocks. It was cheaper, faster, and safer. An underground canal was protected from contamination, evaporation in hot weather, and sabotage. Aqueduct bridges were built only as a last resort when it was necessary to cross a river or a deep valley. The secret of the aqueduct was not in the arches, but in gravity. The entire system worked exclusively by gravity. This required incredible precision in calculations from the engineers. The canal had to have a constant, very slight slope along its entire length. A harabat was used to calculate the slope, the same long water level used in road construction. The slope was minimal, only a few centimeters per 100 meters, or about 1/3000. Too much slope would have caused the canal to be destroyed by the flow. Too little would have caused the water to stagnate. Engineers had to route the canal around mountains or through tunnels, maintaining this precise gradient. It was a titanic task of leveling the terrain. Sometimes, to avoid building a giant bridge, they used an inverted siphon system. Water was fed through lead or stone pipes down the slope of the valley and lifted to the other side under pressure. This method required very strong pipes capable of withstanding the enormous pressure of the water at the lowest point. This proves that the Romans had a perfect understanding of the laws of hydraulics. The aqueduct itself, through which the water flowed, was a concrete trough. Its walls and bottom were covered with a waterproof mortar called opus signinum, which was made from crushed ceramics and lime. This composition prevented water from seeping through and becoming contaminated. The quality of the water at the source was carefully checked. The Romans valued clean, cold spring water. In the city, the water flowed into a distribution reservoir, the castellum, from where it was distributed through a system of lead pipes to public fountains, baths, and the homes of wealthy citizens. The construction of an aqueduct was one of the most expensive and complex projects a city could undertake. It required huge investments and the involvement of the best engineers. However, the result was worth it. The aqueduct instantly transformed a provincial settlement into a full-fledged Roman city, a center of civilization. Nothing demonstrates the engineering power and speed of the Romans like the construction of amphitheaters. The most famous of these, the Colosseum in Rome, was built in less than 10 years, a time frame that is impressive even today. By comparison, many medieval cathedrals took centuries to build. This speed was achieved through a combination of three factors: ingenious materials, modular construction, and flawless logistics. Unlike the Greeks, who carved their theaters into hillsides, the Romans learned to build them on flat ground. This was made possible by two major inventions: Roman concrete and the widespread use of arches. The Colosseum is essentially a skeleton of stone arches filled with concrete vaults and floors. The structure was modular. The entire amphitheater consisted of repeating sections or cells. This allowed construction to proceed simultaneously on multiple sections. While some workers erected stone arch supports, others poured concrete vaults on the lower tiers. This conveyor belt assembly system was the key to speed. Construction on such a scale required incredible logistics. Tens of thousands of tons of travertine for the outer wall and supporting arches were delivered from quarries 20 kilometers away. A special road was built for this purpose. Countless amounts of stone, sand, and porcelain for concrete were delivered by barges and carts. The organization of labor was of the highest standard. Thousands of workers were divided into specialized teams. Some quarried stone, others transported it, others were masons, others were concrete specialists, and others were carpenters who built formwork and scaffolding. Everyone knew their task and the process did not stop. The use of Roman concrete was a decisive factor. It was cheap, could be produced on site, and did not require as much skill as stonework. The concrete arches supporting the rows of seats were relatively light and incredibly strong. The engineers of the Colosseum thought not only about strength, but also about the logistics of moving people. A system of 80 entrances and exits, called vomitoria, was designed so that 50,000 spectators could fill the amphitheater in 15 minutes and leave it in just 5. These corridors and stairways were part of the concrete structure, cast as a single unit. The speed of the Colosseum's construction was also a political statement. The new Flavian dynasty, which had come to power, wanted to give the people the largest entertainment venue in the world as quickly as possible. It was a project to which all the resources of the empire were devoted. In the provinces, amphitheaters were built just as quickly, often by local legions. The standardized design, an elliptical arena surrounded by tiers of arches and concrete vaults, made it possible to replicate the project throughout the empire. The very fact that the Colosseum has stood for 2,000 years, surviving earthquakes and being dismantled for building materials, testifies to the quality of its design. It is a monument not to architectural sophistication, but to an engineering system, a system of logistics, standardization, and ingenious use of materials. Roman engineers did not have laser levels or excavators, but their set of tools was surprisingly effective and accurate. It was these tools, from simple hand tools to complex machines, that allowed them to carry out their grandiose projects at such speed. Success lay in having the right tool for each task. Surveying instruments were at the heart of everything. We have already mentioned the gram for marking right angles and the korobat for leveling slopes. There was also the libellum, a simpler level similar to the modern one, in the shape of the letter A with a plumb line. These instruments allowed for quick and sufficiently accurate marking of foundations, roads, and camps on the ground. For earthworks, the legionnaires used a universal tool called a delabra. It was a heavy pickaxe with one end pointed like a pickaxe and the other flat like a cleaver. This tool could be used to chop roots, break soft stone, and dig hard ground. In addition, they used shovels and woven baskets to carry soil. When working with stone, the Romans used a full set of tools familiar to modern masons. They had iron chisels, hammers, wedges for splitting rock, and saws. To cut large blocks, they used saws with abrasive sand poured into the cut. It was a slow but effective technique. The real breakthrough in the speed of construction of multi-story buildings, such as amphitheaters and aqueducts, was associated with the use of lifting cranes. The Romans improved on Greek cranes, creating powerful machines powered by muscle power. The simplest was the trispastos with 3 blocks, which allowed one person to lift a significant load. For really heavy blocks weighing several tons, the polyp was used. It was a complex crane with a system of 5 or more blocks, which was driven not just by a winch, but by a huge squirrel wheel. One or more workers walked inside this wheel, creating enormous traction. The availability of such cranes completely changed the pace of construction. Engineers did not need to build massive earthen embankments to drag the blocks up, as they did in earlier eras. They could quickly lift and install stone blocks and beams at great heights. To drive piles during bridge construction, they used copras. This was a frame along which a heavy load slid, lifted by a winch, and then dropped onto the pile. This technology made it possible to quickly create reliable supports for bridges, even on unstable ground. The Romans were also masters in the manufacture and use of hydraulic machines. They used Archimedes' screw to drain pits and mines. They had water wheels that not only ground grain but also powered sawmills. This set of tools, precise measuring instruments, versatile hand tools for mass production, and powerful lifting mechanisms, was perfectly balanced. It allowed the army of engineers and legionnaires to work as a single, well-coordinated mechanism, turning blueprints into stone and concrete at an unprecedented speed. 2,000 years is a period of time that reduces most human creations to dust. However, throughout Europe, North Africa, and the Middle East, there are still bridges that can be walked on, aqueducts that look almost ready for use, and roads that serve as the foundation for modern highways. The legacy of Roman engineers has proven to be more durable than the empire itself. The main reason for this longevity is excessive quality. The Romans built not for decades but for centuries. They built their structures with a margin of strength that seems wasteful from a modern perspective. The foundations of roads and buildings went meters deep, and the walls were several times thicker than required by calculations. The second factor is materials. We have already talked about the genius of Roman concrete based on pozzolan. This material does not simply not deteriorate over time, it becomes stronger. Chemical reactions that began 2,000 years ago continue to this day, making the structure more monolithic and resistant to aggressive environments. The third secret is a brilliant understanding of physics and mechanics. The Romans did not simply copy the arch, they understood its essence. Arches and vaults are structures that work under compression, and stone and concrete work perfectly under compression. They learned to distribute weight so that their structures support themselves. Roman engineers were obsessed with fighting the main enemy of any builder: water. Roads had a sloping profile and drainage ditches. Building foundations were insulated. Aqueducts had inspection wells for cleaning and repair. They understood that the height of a wall was not as important as the dryness of its foundation. The speed of their construction was not synonymous with carelessness, as is often the case today. On the contrary, speed was achieved by perfecting each stage. Standardization, combined with discipline and the right materials, made it possible to build quickly and at the same time for centuries. This legacy is not only in physical objects. The main thing that Roman engineers left behind is the approach itself, the system. They were the first in history to create the profession of engineer as a civil servant. They wrote the first textbooks on architecture and construction, such as the work of Vitruvius. They proved that logistics and work organization are no less important than the genius of the project. Modern large-scale construction, military engineering, standardization, and quality control systems all have their roots in the practices of the Roman legions and architects. When we look at the Pont du Gard or the Colosseum, we see more than just ancient ruins. We see the triumph of a system that was able to mobilize thousands of people, standardize materials and processes, and apply simple but effective technologies to achieve grandiose goals. Their speed was not a miracle, but the result of the entire power of a vast empire being focused through the lens of engineering thought. They built quickly because they did not know how to build any other way. For them, construction was as much an act of world domination as war or lawmaking. We have taken a journey into a world where the shovel was as important a tool as the sword, and where the speed of construction was key to the empire's survival. We saw that faster did not mean worse for the Romans. On the contrary, their speed was the result of impeccable organization, standardization, and the use of revolutionary materials such as pozzolan-based concrete. Their roads, aqueducts, and amphitheaters are not just monuments to the past. They are an eternal rebuke and at the same time, a textbook for modern engineers. They prove that discipline, a systematic approach, and a deep understanding of materials can work wonders that are beyond the reach of time. Roman engineers did not build for themselves. They built for eternity. What do you think about these engineering solutions? Which of the technologies of ancient Rome, concrete, roads, or aqueducts, do you find most impressive? Suggest topics for future videos that you would like to see on our channel in the comments. And don't forget to subscribe so you don't miss out on new research into the mysteries of the past.